Hello everyone, I would like to introduce our paper Every Mutation Should Be Rewarded, Boosting Photo-Localization with Mutated Predicates. My name is Xue Zhengxue. I'm from University of New South Wales. This work is done in collaboration with Changwei Zhou and Professor Jingling Xue. Well, given a buggy program and a test suite, photo-localization aims at finding faulty locations automatically. It usually calculates a suspiciousness score for each program location and ranks them according to their scores. There are various photo-localization techniques which are based on different information sources, such as spectrum or program coverage, mutation, or slicing. One of the most popular photo-localization family is based on spectrum or program coverage. It first records which test case covers which statements and calculates suspiciousness score by formula. The statement covered by more field and less pass test cases is more likely to be faulty. However, this technique is too coarse-grained, and using program coverage information only is not enough. Another popular photo-localization family is based on mutation testing. It first mutates each suspicious statement by applying some predefined mutators, such as changing a plus operator to a minus operator. Then it produces many mutants and rerun test cases for each mutant. It ranks suspicious statements according to the following hypothesis. Mutating faulty statements is more likely to make failed test cases passed than mutating correct statements. This technique is fine-grained but time-consuming because there are many possible mutators and statements, resulting in a large search space. It may take hours to locate one fault. Well, it's challenging to develop an effective and efficient photo-localization technique. First, photo-localization with a single information source, such as program coverage, is ineffective. Second, photo-localization with multiple information sources is promising, but how to combine them? Recently, researchers run different techniques independently and try to combine them by machine learning. However, we will face an efficiency and effectiveness dilemma when we combine multiple sources. Well, to combine multiple sources, we hope to make full use of their advantages during the analysis process, instead of running them independently. Also, we hope to reap the benefits from mutation testing in a time-controlled manner. For example, we could first get a preliminary ranking based on spectrum only. Then we use it to guide the mutation testing. For example, we could selectively mutate statements according to their preliminary ranking. Then we can combine two information sources to generate a final ranking. Before we talk about our solution, I would like to introduce Predicate Switching, a lightweight mutation testing technique. Well, the predicate switching mutates only predicates. Since there are only two possible states of a predicate true or false, this technique is lightweight. Well, a predicate P is critical if switching P overturns any failed test case. Then we can find the faulty statement by manually examining its root cause, which can be assisted by dynamic slicing. However, there are several limitations when we use predicate switching only. Firstly, there may not be any critical predicate. Secondly, we cannot further rank suspicious statements even with dynamic slicing. We propose FLIP, a photo-localization technique with inferences from predicates. Firstly, we run a pre-analysis using a standard spectrum-based photo-localization workflow. After we get the preliminary ranking, we use it to guide the selection of predicates. For example, we can select top 10 predicates in the ranking list. Then we use mutation testing to classify them into critical and uncritical predicates and make mutation inferences from them. Then we integrate the mutation inferences into the original spectrum and build an enhanced spectrum. Then we use the same formula to calculate a final ranking. Well, the tricky part is the mutation inference. For critical predicate P, we collect all the statements that may affect the values of P and regard them to be suspicious statements executed by a failed test case. And for an uncritical predicate P, we collect all the statements that only affect the values of P and regard them to be less suspicious statements executed by a past test case. Then we can integrate these mutation inferences into the original spectrum to build an enhanced spectrum and use the original spectrum-based photolocalization formula to get a final ranking. We use Defects4G to evaluate our flip, which contains 438 real-world false, and we use two common metrics in photolocalization and 7 spectrum-based photolocalization techniques as our baselines. Well, generally, every baseline model can benefit from our flip. For example, flip outperforms 7 baseline models by 21 to 46% for top 1. Well, as for the overhead, the total overhead for one fault is 85 seconds on average. Well, the time spent on mutation testing is related to the number of failed test cases, and the time spent on mutation inference is related to the program dependencies and the call graph. Our flip has several limitations. First, it works in statement level, but fails to distinguish omitted and faulty statements. Second, a failed test case may contain several failed subcases. If mutation testing overturns only one of them, the test case will remain failed, and our flip will mistakenly mark the corresponding predicate as uncritical. Third, like other photolocalization techniques, our flip cannot handle faults with multiple faulty locations. For example, the spectrum-based photolocalization will mistakenly read the ranking of the convergence of branches if faulty statements reside in multiple branches. And mutation testing has to mutate multiple statements at the same time to overturn test results. Well, that's all. Thank you.